The shortest even cycle in the graph to the left has length 6. The graph to the right doesn't have any even cycles at all. In this video, I'll try to explain how to find such a thing in polynomial time, based on joint work with Andreas Björklund and Petteri Kaski. Just to make sure we agree what the problem is, our example graph contains 8 different cycles. 4 have length 3, there's none of length 4, but there are cycles of length 5, 6, 7, and 8. An even cycle is a cycle of length, say, 6 or 8, so an even number of edges. And the shortest even cycle, the one we're looking for, has length 6. Let's also go back to the other graph. As I promised, it contains only cycles of length 3, 5, and 7. Note that both our examples are small enough that we can systematically investigate all cycles in the graph, but in general, graphs have an exponential number of cycles, and checking them all becomes infeasible. So what I want to tell you about in this video is that the shortest even cycle problem can be solved faster than by investigating all cycles. In fact, that it can be solved in polynomial time. Now, you may reasonably think that this sounds like a pretty easy problem, so let's get a feeling for this by looking at some well-known variants. First, let's drop the parity condition and just remind ourselves how to find a shortest cycle in a graph at all. Our starting point, mainly because it will be useful later on, is the adjacency matrix A of the graph G. Recall that there's a 1 in row 4 and column 8 in A because G has an edge from 4 to 8. Consequently, the square of A accounts for the walks of length 2 in G. For instance, the green walk from 1 to 5 via 2 leads to a 1 in row 1, column 5 of A squared, which is the dot product between row 1 and column 5 in A. Similarly, and now it gets interesting, the blue walk, connecting vertex 3 back to itself, appears as a non-zero diagonal entry in A cubed. Let's do this all the way to A to the power 6 and reintroduce our quarry, the green 6 cycle. We can trace along it, maybe starting at vertex 1, and duly observe the corresponding ones in the matrix powers all the way to the entries in the diagonal entry 1, 1 of A to the power 6. Note that the diagonals in both A squared and A to the power 4 are all 0, and that A to the power 6 is the first even matrix power with a non-zero diagonal. And this sounds a bit too good to be true, and indeed it is, because of walks, like closed 6 walks, like the one shown here in red, which is self-intersecting, so it's not a cycle, and we don't want to find it. Still, this known observation is worth spelling out. The trace, that is, the sum of the diagonal entries of the kth power of the adjacency matrix, is non-zero if and only if there's a closed walk of length k. Note that this expresses a combinatorial question about graphs, in particular the existence of walks, as a linear algebra question about matrix powers and traces. The technique that I'm advertising in this video has the same flavor. Let's have a closer look at the relationship between closed walks and simple cycles. First, we observe that a closed walk need not be simple. At the top, you see an example of a closed walk of length 12 that repeats a vertex. However, such a self-intersecting walk must decompose into strictly shorter closed walks, and in this example our 12 walk decomposes into closed walks of length 5 and 7, both of which are simple. In particular, a shortest closed walk cannot decompose into shorter walks and therefore must be simple. So the problem of finding a shortest cycle in a directed graph is the same as finding a shortest closed walk. Therefore, it can be done in polynomial time, for instance like I just showed you by computing traces of powers of the adjacency matrix. Of course, standard graph traversal algorithms such as breadth first search will do the same thing for you. There are many ways of seeing this. Maybe less obviously, this argument extends to the odd case. Indeed, a shortest odd closed walk is also simple, and this relies on a parity argument. An odd number can't be decomposed into a sum of even numbers. Thus, the same approach as for the shortest cycle problem also works for the shortest odd cycle problem. And to appreciate this argument, note that it failed spectacularly for the even case. In fact, here is a perfectly respectable shortest even closed walk of length 12, but as we can see, it is not simple, and it decomposes into two odd cycles, and in fact this graph doesn't contain any even cycles at all. Thus, the entire approach doesn't get us anywhere, apart from maybe realizing that the even cycle problem is very different from the odd cycle problem. Let's briefly go back to our overview of problem variance. We saw that the shortest cycle problem is easy and that we got the shortest odd cycle problem for free. Let's look at another simplification, the shortest even undirected cycle problem. Back to our graph, and let's get rid of the orientations. Take two copies of the graph and connect each vertex to its copy with those gray edges. Let me look for a maximum weight perfect matching in the resulting graph. I choose weights so that the gray edges are really attractive to the matching, and clearly the maximum weight matching will pick exactly those edges. Now let me subdivide one of the green edges. Any perfect matching has to match the new leaf with the other end of the subdivided edge, but then the mirror vertex to the matched vertex can no longer use the attractive gray edge and must look for a match in the red graph. This process continues, alternating between picking a red and a green edge until it can finally match the other new leaf. The result is an even cycle in the original graph. And the maximum matching will still try to find as many gray edges as possible, here 3 of them, so the even cycle it finds is necessarily shortest. So, shortest even undirected cycle reduces to maximum weight perfect matching, and a famous and highly non-trivial algorithm by Edmonds solves that for us. So now there's just one obvious simplification left, the even cycle problem, that is the decision version of the shortest even cycle problem. For this, we go back in time more than a century. In 1913, George Polya published an innocent exercise in Archiv der Mathematik und Physik about determinants. I'll spare you the convoluted phrasing of the German original. What Polya asked is the following. Recall that the determinant is defined as a sum of products with an intricate rule for sign changes that is the bane of every linear algebra student. But by strategically placing a minus sign at the bottom left entry, we can transform any 2x2 determinant into a sum of products without sign changes. So for 2x2 matrices, the determinant is just the permanent, after some sign changes. Polya's exercise was then to determine if this could always be done. The answer is no, by the way. But it leads to a nice algorithmic problem. Given a matrix, modify its signs so that the determinant of the original matrix equals the permanent of the modified matrix. For some matrices this can be done, like here, for others can't. And today we call this Polya's permanent problem. It turns out to be algorithmically really interesting and equivalent to a bunch of other problems. Let me show you half a dozen of them. Given a matrix of signs and 0, are there integers consistent with those signs so that the resulting matrix is non-singular? Another example, most relevant to the rest of the talk, given a matrix, is its determinant equal to the permanent? This is a yes instance, by the way. Both functions make 4. Given a hypergraph, such as the 3 regular Fano plane here, can the vertices be colored so that no hyperedge is monochromatic? I've tried here, you can see, and failed. Note that there's an all-red hyperedge, and this particular instance indeed does not allow any balanced coloring. So this is a no instance. Given a bipartite undirected graph, does it allow a so-called Pfaffian orientation? I'm not going to define that for you, but here the answer is yes. And finally, the even cycle problem. Does a given graph contain an even cycle? This one, as we remember, does. Here is one of length 8. It was open for many decades whether this problem could be solved in polynomial time, until this was settled in the positive in a real tour de force by 2 different sets of authors a quarter century ago. Let's go back to the problem at hand, the shortest even cycle problem. I've tried to convince you that the variants of this list can all be solved in polynomial time, sometimes with very straightforward ideas and sometimes not. Now let me tell you how to solve the shortest even cycle problem in polynomial time. From our brief excursion into related problems, we'll take with us two important ideas. We'll start by the well-known connection between cycle covers and permutations. First, we equip G with self-loops at every vertex. This corresponds to adding ones to the diagonal of A. The permanent is a sum over all permutations of the vertices. In this case, there are 9 vertices and thus 362,880 different permutations. Let's look at just one of them, for instance 7, 3, 6, 1, 5, 2, 4, 8, 9. In A, this permutation picks out a specific pattern of rows and columns corresponding to putting non-attacking rooks on a chessboard. For instance, in row 7 it picked column 4, which has a 1. And in the graph, this corresponds to picking the edge from vertex 7 to 4. A different permutation, like this one, might have mapped 7 to 8, but there is no edge there, and the corresponding matrix entry has a 0. The identity permutation always contributes and corresponds to the cycle cover given by the self-loops. In total, in this instance, there are 16 permutations that make it, by picking only once, or outgoing edges that actually exist. So, since everything is finite, these permutations correspond to cycle covers. So, the 16 permutations that actually contribute to the permanent each correspond to a cycle cover. Here's all of them, and let's focus our attention on just 6. Each cycle cover consists of a number of disjoint cycles, or components. Let's denote this number by kappa. Now, by a parity argument, if each of the cycles in a cover is odd, then the number of connected components has the same parity as the number of vertices in the graph. This is easy enough to see for the all self-loop cover, but it holds in general. Conversely, the covers containing an even cycle all have an odd number of components because the total number of vertices in this graph is odd. Let's look at how each of these cycle covers affects the permanent and the determinant, respectively. Clearly, the green cover contributes to the permanent. In fact, the corresponding term is exactly 1, but let me write it in this clumsy form just to see what's going on. On the other hand, the green cover contributes negatively to the determinant. Things are notably different for the red cover, which contains only odd cycles. This one contributes to the permanent and the determinant with the same sign. And now the magic happens. When I subtract the determinant from the permanent, the red terms cancel. What is left are the contributions from the covers that contain an even cycle. In fact, each of them contributes exactly twice. That's going to be important later. We have arrived at one of the many equivalent formulations of the even cycle problem that we saw before, and this one is the one due to Vazirani and Giannakakis. Even cycles are the same as permanent minus determinant. This characterization is the starting point of our algorithm. We now introduce a formal variable y and put that on the diagonal entries of the matrix. To be precise, A is now the adjacency matrix of the original graph without the self-loops, and we've added the identity matrix multiplied with the variable y. Now, what happens if we compute the permanent minus the determinant of that matrix? As before, only the covers with even cycles contribute, but the contribution is now no longer just 1, but it is a product of 1's and y's. For instance, this cover consists of an 8 cycle and a single self-loop, contributing a single occurrence of y to its term. The cover consisting of a 3 and a 6 cycle picks no self-loops and just contributes a boring old 1. But our quarry, the 6 cycle, also appears in a cycle cover where every vertex not on the cycle picked its self-loop. And that cover contributes a whopping y cubed term. So our per minus det function applied to the matrix A plus yi is a polynomial in y, all coefficients are even, and the highest order term corresponds to a shortest even cycle. We have arrived at an algebraic characterization of the shortest even cycle problem. Algorithmically, this still looks quite useless because the permanent is famously difficult to compute, but let's soldier on. First, let's get rid of the polynomial, and this is quite standard. The polynomial we're after has degree at most n, so we can interpolate its coefficients from n+1 evaluations. We just need a field so that we can divide, and the field has to be large enough. Let's recall some basic facts about computing the permanent. Famously, the permanent is hard to compute, in fact hard for the counting class number p. On the other hand, the permanent is easy modulo 2. This is because it equals the determinant, -1 is the same as 1 modulo 2, and the determinant famously can be computed in polynomial time by a method due to Gauss. Valiant also established that this easiness is inherited to some degree to larger powers of 2. For instance, the permanent modulo 4 can be computed in polynomial time as well. Again, this looks quite useless. The integers modulo 4 are not a field, so we can't interpolate, and there are only 4 of them. Still, the intuition behind Valiant's algorithm is useful for us to understand, so let's spend some time on it. The permanent is multilinear, so when I add row I to row j, the resulting matrix equals the original one plus some error term that contains the same rows twice, much like what we're used to for the determinant from linear algebra class. For the determinant, this error vanishes, but there's no such luck for the permanent. This is exactly why Gaussian elimination fails for the permanent. But all hope is not lost, because the error term contains 2 equal rows, so the expansion of the permutations will contain every term twice. In particular, the error term is an even number. And this means, after maybe a bit of head scratching, that we get 1 bit for free, so to speak, and we can compute the permanent of these matrices modulo 2, not 4. Thus, we can mimic Gaussian elimination, albeit with more labor, transforming the original matrix into upper triangular form. Each of the O of n squared many error terms is even, so they can be computed in polynomial time themselves. The permanent of the final triangular matrix at the bottom left here is just the product of the diagonal entries. Be that as it may, neither of these two structures, the integers modulo 2 or modulo 4, completely fit our purposes. We need something fancier, namely a large finite field. This is usually realized as the field of monovariate polynomials with coefficients modulo 2, modulo an irreducible polynomial. If you haven't seen this before, it looks a bit scary, so let's take a concrete example. The finite field, GF for Galois field, on 8 elements. You can think of that as these 8 very concrete polynomials with 0, 1 coefficients. Or alternatively, you can view these things as bit strings of length 3 by just looking at the coefficients. Addition and multiplication are defined as usual for polynomials, except computation is modulo x cubed plus x plus 1, which is this polynomial that cannot be decomposed into smaller polynomials modulo 2. These always exist, and you can find them in randomized polynomial time. So the resulting algebraic structure solves 2 of our problems. It's large enough, and it's a field. To see this as a field, you can look at the multiplication table, and you can see that the unit polynomial appears in every row except the first, so you can divide. On the other hand, the structure has characteristic 2, which you can also see in one of the tables, the addition table. The diagonal in the addition table is all zeros. So the trick is now to extend this finite field into a larger structure, where the polynomials now have coefficients 0, 1, and 2, and 3. This structure contains all the polynomials in the original Galois field, but it also contains things like 2x squared plus 3x. So everything on the left side of the field also exists on the right side in the ring, and there's also a way to project the ring elements back into the field in the obvious fashion by taking the coefficients modulo 2. So we can move between these two algebraic objects at opportune times. And our algorithmic insight is now that the permanent minus determinant polynomial can be computed by carefully jumping or alternating between these two structures whenever we need one of the properties. And they are quite different. In particular, the ring has characteristic 4, which is good when you want to find something that is always even. And most importantly, we present an algorithm for computing the permanent in this structure. An algorithm that follows the same melody as the modulo 4 construction by Valiant that I just showed you. Let's take 10 steps back and try to get some kind of overview of the entire algorithm. Begin with the graph's adjacency matrix and translate that into the finite field. Then put a field element in the diagonal and compute the permanent minus determinant of the resulting matrix. This computation happens in a different algebraic structure in the ring, allowing us to mimic Valiant's algorithm. The result is a value which we reinterpret as a member of the field, and that gives us now a single xy pair in the field. We do this n+1 times and interpolate the coefficients of our polynomial, which was a polynomial in y. The highest order term in that polynomial then tells us the length of the shortest even cycle in the original graph. There are a bunch of details missing here. What if the number of shortest even cycles vanishes modulo 2? There could be 2 of them. What I showed you here only works if there's a unique shortest even cycle. Or how do we actually recover the cycle itself rather than just learning its length? But these things can be solved by pretty standard techniques, which I won't show you here. Everything is carefully laid out in the paper, which I hope you'll enjoy reading. Thank you very much for listening.